מהו מורי ומהו מה? מהו לתת לנו done? Okay, so let's start. So last week we talked about different type of quantitative imaging and anatomical imaging, and today we're gonna discuss one in particular, diffusion imaging, which is very useful in measuring brain anatomy. So we'll look at that in more details. We'll look first on the phenomena of diffusion and how we measure it, and then we try to talk about the usage. And about the usage, and in particular in the end we're going to look about something called tractography, which is a way to identify pathways in the brain and create this kind of brain connectivity networks. Okay, so let's just start with a short summary of last week. As I said, we discussed T1 weighted and T1 and other quantitative methods and weighted methods, right? And we said that it could be that we have some kind of a summary of the physical phenomena, right? In a way which we don't know exactly which is which, but we have some weighting of one of the strong weight of one of the phenomena. In this case, this was a T1 weighted or quantitative maps. And today we're going to look in this bento on this DT, diffusion imaging, okay? So diffusion tensor in this case, but we're going to drill into one of them. And I also mentioned last time things that we could have done with those measurements. Just recapping and remind you where we were last week before we getting into the new things. It's too cold in here? It is? Okay, so we were mentioning cortical thickness last time, right, as a way to identify the cortex and the thickness of the cortex, and that was some kind of a parametric math that we could measure across subject. And we mentioned a voxel-based morphometry, which was a way to register all the brain to each other and map the amount of change that is needed to take one brain to some canonical brain. And that was a measure also to measure differences between subjects. And then I told you a little bit about measurements like quantitative imaging, and I was saying that many of them were trying to measure myelin, trying to measure the myelinization of axons using quantitative methods, for instance T1. Okay. So another method that is really useful for measuring, in particularly the white matter, is diffusion, although it's not directly sensitive to myelin. We're going to see what it is related to exactly. So what is diffusion? Just a phenomena? Someone wants to just give me like a fast definition?
particles?
Movement of particles. In what way?
In what is described as Brownian motion.
Brownian motion. So without any coherent order or direction, right? And so that's true. And so if our particles are a water molecule, right? The protons of the water molecule, that's what we are sensitive to. And as function of time, we can assume that if we have some water molecule, let's say they are tagged somehow with our measurement, we assume that the signal, as they diffuse and moving in space, we assume that what would happen to the signal? We're going to lose it. It's going to decay, right? Because if we tag them here, then they move to somewhere else. We cannot see them anymore. So there will be a phenomena of signal decay as function of diffusion. That's the main physical phenomena that we are measuring. And in particular, in biological, so as you said, diffusion might be Browning. There's a Browning motion, and when there is no obstacle, we assume free diffusion that will go and the change will be in all dimension. Here it's 2 dimension, but it will be kind of equivalent, will be the same in all dimension, and the signal will be lost, or this water will diffuse freely in all orientation and all dimension, right? This one is 2D. But if there are obstacles, if we are inside biological tissue, which have barriers, let's say, what kind of barrier we might have? Membranes. Membranes are the main barriers in biological tissue. Then we can expect that the diffusivity will be reduced because of those barriers. And if this orientation or organization of those barriers, then we might have greater diffusion along where there are less barriers versus the other dimension, right? In this case, axons, right? There will be more diffusion in parallel to the axon versus in perpendicular to them. We will measure this, so we will have a loss of signal due to diffusion, which it will be lower in perpendicular to the axons because of that reason, right? Wait. So how can we measure that? So you remember we had this option to add gradients, which adding what to the system? What a gradient in magnetic field does? Disorder. It's making.
Disorder the spin. We know that it's organized disorder. We know how to fix it later on.
Great. So it's dephasing them in some order. It's creating this inhomogeneity in space, right? In the magnetic field. So spin will dephase faster, or dephase in a different order according to this direction of the gradient that we put. Okay. So say we have here spins. Let's see them again. And say they are all oriented in the same direction. They generate a signal. Now I'm going to put so we have here 3 voxels or something like that. I'm putting here a gradient. So this here they will there is some dephasing, right? And here it's even greater, and so on. So we have now dephasing as function of this gradient, function of this inhomogeneity of the environment. And now let's think that there will be I will give it some time. Some of them will diffuse, some of them won't. Let's say in here there's a lot of diffusion. Some of them are just going to move. Right? They're now they move. They're in a different voxel, something like that. So now when I'm essentially rephasing them by creating the opposite gradient, okay, I will have a reduction. So both those guys, because they didn't move at all, it's like this is like kind of an imaginary scenario where nothing happened for these guys. Okay, so they just back. So I have maximal signal. In here, some of them moved, and so lost, and so we're going to have a decay in the signal here. So we have a contrast, a diffusion contrast, right? Because we have now a fact which is sensitive to the time we wait for them to diffuse. As we wait longer time, we have more diffusion, more signal will be lost, and according to how much they can diffuse, we will have greater signal decay because of diffusion. Is that clear? That's the basic. That's also that's the physics of this thing. So was it clear? Should I say it again? Everybody feels it's okay? Great. Okay. So what we're doing, we're using the sequence that we described in the first class, which we call Spinnaker, the 90 and then the 180, and we're adding on top of that a gradient before and after the 180, the one we just discussed. Okay, and that will allow. They notice that they're actually in the same direction, not in the opposite direction. No, because there is a 180, it's like to do it in the opposite direction, because 180 also flipped them. And so that's how we essentially getting this diffusion. And you can do it in X, Y, and Z, or combination of X, Y, and Z. That will allow us essentially to sample the diffusion. So what I just showed you was in one direction, right? But I can do the same thing, let's say, in this dimension, right? And then I will encode the diffusion in one dimension, and in another, in the X dimension, in the Y dimension. I could do it in the Z, and I can do some kind of combination of X and Y, right? Like that, I will be able to do measurement of diffusion all in 3D. Fine? Is that okay? This one was in X. I could have done it in Y. Could have done it in Z. And I could do a combination of that. And then I would have a diffusion measurement in 3D. Okay. So the typical Spinnaker equation, if you remember, was an equation was depend on T2, was a T2 measurement. So magnetization was dependent on T2, and that's coming from the clock equation. And to that we add now another phenomena, another exponent, which is decay. It's function of diffusion, so diffusivity. So how much water actually, so this parameter called diffusion coefficient, which summarize how much water will diffuse as function of time, and some B value, which we're going to identify in a second, which define how strong was the gradient, or kind of parameterize the gradient, how much diffusion weighting we add to the system. Okay. So before until now, we were ignoring this, that we had an equation that was depending only on T2. Now we say T2 and diffusion. We're going to talk only about this aspect of the equation today. Okay, and this is the article. Okay, so sometime we're going to call this parameter the Affarin diffusion coefficient. Why I'm saying apparent? Does anyone have a notion? Why it's apparent? Is it the real? What is? Well, diffusion coefficient is something is well defined in physics, right? It's
Theory, you can't prove it, Brownian motion.
well, I can measure it. I can measure it, but why do I say it's apparent diffusion? Well, that's also often in normal diffusion, right? There is something about this measurement which is it's sensitive to diffusion, but not exactly measuring the real diffusion as defined by Einstein. Actually. And the thing is that it actually first it depends on B. So I'm changing the gradient, I might get a different diffusion coefficient. And also, it's not really I'm not going to get a real Brownian. Well, I'm not going to get a real free diffusion because there's going to be barriers. So although this equation is like an equation of free diffusion, what I'm going to measure is something which I'm analyzing with the same equation, but the effect is actually coming from something which is not just normal distribution of diffusion in space, and it will be dependent on the barriers. So it will be both dependent on the biology and on the way I measure it. So with different B values, for instance, different diffusion weighting, I might be getting different diffusion ADC, different apparent diffusion coefficients. So this is the diffusivity as measured with MRI, giving the parameters that I was using. Okay, that's what it means. Okay, so what is this B? So B, we said it's everything that has to do with how we did the experiment, and that has to do with So you can see the people say, oh, the beginning we were like, there was so many people were, the equation in the beginning was very long, it's very parametric. Okay, you know what, it's all constant for my measurement. Let's just call it B. And so it have to do, well, the gyromagnetic ratio with that won't change, right, in a magnet, but the strength of the diffusion gradient I use, so how big they were, the duration I actually open them, turn them on, and turn them off, and the time between the first one and the second, all of those things will change the diffusion that I'm waiting in the system, and I'm just putting them inside this B coefficient. And I will keep it the same in an experiment. Until toward the end, I will say that I will change this B. But for now, we just keep it as constant. We're just going to select something. And most of the people who's doing diffusion measurement, they just say, oh, let's just use B of 1000, whatever, and that's it. Okay? Okay, so this is B. And we said before that we have an exponential decay, right, as function of B. So that means that the signal will decay as function of B, and because this is the equation, I'm putting S0 is everything include the T2 effect because we don't care about it right now, right? And so that means that I can now take a lamp and create a linear equation, right? Which is the lambda of the signal as function of the apparent diffusion and the B value, which make it very easy to fit if I want, right? I actually need one measurement, I need the measurement with, I need the S0, so the measurement without diffusion, and one measurement with diffusion weighting, and I can get the ADC. You see that, right? What is then the prediction? What would happen if I would change the B value? What would happen to the signal according to this equation? As I'm increasing the diffusion, what would happen? What should I expect in terms of the signal, the measured signal? Just look in the graph. Okay, we're going to go down, right? It's going to be reduced. And what is so? Okay, so that's what the equation says. Say you have a stronger B value, maybe stronger diffusion gradient, or longer opening for a longer time, and you would get a reduction of signal. And that sound to you from what we said before about the phenomenon of diffusivity? No? So it's greater diffusion weighting. What do we say diffusion doing to the signal? It's causing a reduction of signal, right? So a stronger B value means a greater diffusion weighting, which means just greater loss of signal. So that was the question. That is the answer. Let's just see that for a second. So this is diffusion measurement in a brain using a fast. We're typically doing it with a fast imaging, which means that the image is kind of coarse. I mentioned in the first slide that there are those methods to measure really fast. The full K space, I called it, if you remember. Never mind. I was mentioning this fast way to acquire the images, and one of the problems of those methods, which we are typically using in diffusion and in fMRI that we'll discuss later, is that the image looks a little bit blurry, but it allows us to measure it along the whole brain. And so this is why it looks a little bit like well, the shape of the brain, but it's really hard to see much more than that, right? I will show you that we can see more. In my screen I see more, but anyway, changing the B value, 1000, 2000, 3000, here, 4000, sorry. You see a really reduction of the signal. And there is actually one phenomenon which is interesting. Look at that. In the beginning, I mean, these things always appear, right? This bright thing here. But as I'm increasing the B value, everything else is like just go, and I'm left only with that. This thing is the optic radiation, or tracks that go from the occipital. I think it's the optic radiation. That's the main thing between the occipital to the front. Okay. And because the diffusion direction is that way, so those tracks go kind of like that. And so so we don't have a actually. Wait. I think it's the opposite. Because we don't have a great reader. Right. We sorry, I confused myself. So we're weighting the diffusion in this direction, and so we don't have a great reduction of signal in here, because all the tracks goes in that direction, and so these things stay bright, versus the other thing which we're losing the signal in other directions, in other region of the brain, and as we increase the p-value, they become more and more exposed. But in general, the SNR reduced. So there is two things that happen in here. I will come back to that. In one hand, it really enhanced the effect of this pathway, the optic radiation. It just pops out. On the other hand, we kind of the SNR in general is being reduced. Okay. So I mentioned in the beginning that we can measure ADC with two measurements, right? So taking a B0, so that's just a T2 weighted essentially, right? B0, without any diffusion weighting, so the B is 0. So we left only with the T2 aspect, so T2 weighted versus one which have some diffusion. That's a typical clinical diffusion weighting, which people use in the clinic. They always do diffusion. That will be about what they do, and they will calculate this ADC from that. And so they have this measurement of apparent diffusion coefficient, and it's surprising. It's very helpful, or not surprising maybe. So here is cases that you might see in the clinic, and the projection is not so great. So I think it's really hard to see that this area is really dark, but it's super dark. ADC. That means that there is great reduction of signal or not so much in here. If the ADC is low, it's you're going. That's true. Yeah. So the diffusion is very short, or there is very little diffusivity, right? So the ADC, the diffusion coefficient, is low. You were right. And so that means that the viscosity in this region, you cannot see it really, but in my screen it looks much better. Or maybe in this, I put the slides for you, so you might be able to see it. The viscosity there is higher, and that's something that sometimes happen both in stroke and in other. So this is edema that's coming from stroke. And actually, I mentioned that is really important to use that in order to identify where we are in the stroke. So that's one of the phases of stroke, and that's been used in the clinic for that, to identify this. This is in the case of cancer, I think. In here you can see that they are, there is area of edema, which the ADC is really high, it's very bright, and then there is an area within which is different in its viscosity. That's actually very useful for clinicians, say, before they're going for a surgery, to know what to expect. Oh, and also the pattern of how it looks kind of allow them to do a better diagnostic, say what we have here. Okay. What is what is going on there? It's probably inflammation that's happened around it, but why? I don't know. Okay, so that was about the measurement of diffusion, the measurement of ADC, a little bit about the measurement of that in the clinic. But if we want to try to look and measure, say, the white matter in different orientation, the white matter, what should we do? You remember this one was with one diffusion measurement. Say I want to go and look at the white matter, and white matter, if you don't know, have different orientation in the brain and so on. So what should I do? What is the next move? Yeah, do it in many directions. And the thought is that an area which have no organization, we would see some isotropic diffusion, so there won't be any directionality. Right? In an area which have anisotropic organization of the tissue, we also would see anisotropic diffusion. Okay? So we will see greater diffusion along the main axis or the main orientation of the fibers, and less so in perpendicular to that. Is that clear? Questions? It's getting hot in here. So we can wait until the break, I think. Maybe everybody will fall asleep until then. Okay, so let's see that. Let's do that. We're starting with the B0, and now I'm going to change. You would see I will change the direction, and we'll see what we see. What is how the image look, and you would see what should we expect if we're changing the diffusion direction. Before I change the B value, and we saw one of the tracks in one direction, and we saw one of the tracks popping out, right? Is bright. Now I'm going to keep the B value the same, but I'm going to change the orientation. What do you expect to see? Yeah, different tracks according to the direction. Exactly that. So in each image, we're going to see things which pops according to the orientation of the fibers in relation to the direction of the diffusion. Here it is. So this is one orientation, and we see areas which really goes down, and other areas which are bright. And now I'm going to change the direction, and the image looks slightly different. And in general, this is what so now I'm like turning it in all directions. So it's a movie, right? And you can see different tracks changing, right? And this is a nice image. This is the sagittal one, so you can see the corpus callosum, and there is a moment which has become bright, and then it becomes dark, right? So it really becomes bright when the direction of the diffusion is. Yes. Great. So what do I need to do now? I have many measurements of diffusion, many orientations. What should I do now? What is the next move? Should I just do ADC for each of them, or what should I do? What would you do? You have many measurements. So you have many measurements, and you want to create some kind of simplify what?
For each box that I can do an average for all of these.
You would just average them all together. That's one option. That is I'm not going to use the word. I want you to say the word. You have many measurements. You're in LSEC. What would you do? You will do a model. You will try to model them. You will try to do some kind of a summary statistics. Average is 1. You might do slight more than that. Try to do a summary statistics of all those measurements, and that is so we need a 3D model for the diffusivity, right? That's going to be our next move, and the tensor model is basically that. So you heard about the tensor model, you read about the tensor model, so something about it. That's what it is. It's a 3D model of diffusivity, right? So before this was the equation for one orientation. We now would like to have we essentially can represent any orientation with a tensor, right? So so it's not B a function of D, and we have B and D in each orientation X, Y, and Z, and X, Y, X, Z, and Y, Z, right? And so to say that is essentially to say a 3D ellipse, which is a tensor. Okay, so something with a shape. We can now talk about the diffusivity as this 3D ellipse. Okay. That's okay? Before, yes? This is essentially how many measurements you need in order to calculate a tensor, and you need 6.
So what is like, but in the middle of X, Y, B be XY, like it could be.
So it's the weighting of the diffusion in XY. So you need a measurement in so and you can turn them both of them together, and then I will get the diffusion in XY dimensions, some kind of like in say in the middle or not in the middle between X and Y. Plane, or not a plane, a vector in between them. And so our diffusion is now a 3D, is a matrix, right? And because it's symmetric, we have here 6 parameters that represent the diffusion in all directions. Each diffusion in each direction can be described as the combination of those diffusion coefficients. This tensor has many interesting phenomena or useful phenomena. Essentially, we can describe it as 3 eigenvectors that describe the space. Okay, so the x, y, and z of where the diffusion is actually going to. It might not be the x, y, z of the image. It might be. And we can say what is the projection for each of the dimensions, and that will be the eigenvalues, lambda 1, lambda 2, lambda 3. Okay? And we sometimes we would look on the first one. That will be we're going to call it the axial diffusivity. So the size, it's a size, right? It's a value. So the size of lambda 1, we'll name it the axial diffusivity, and those two will be called typically we're going to take both of them together, and we're going to call them the radial diffusivity. The mean of those two will be called radial diffusivity. What else do I have in here? I have a few more things to say about. I'm going to show you what we do with the mean and something about the statistic between the size between those values called functional anisotropy in 2 slides. Just to show you that tensors are useful and you can make many shapes with them. So this is do we play with it in the we're not going to play with it. We remove that. Yeah, it was too long. But if you want, you can ask for it. We have it. So essentially, if we have nothing if we have only values on the diagonal and are in the same size, we're going to get a ball, right? And if one of them is greater than the others, we're going to get an ellipse. Just want to give you some kind of a feeling of how things are going to change with this tensor shape. And if we add this xy or the xy coefficient, we're going to start to get also orientation in space. Right? We're going to move it in space. Okay, and we can move from a ball to a cigar shape, right? From a ball to a line, essentially. If it would be 1, 0, 0, that would be. Okay, if we average the three values, the C lambda, we're going to get something called mean diffusivity. It is very similar to apparent diffusion, but just the average all over. That's the average that you were mentioning. So I could average everything, and I will get the mean diffusivity, which is essentially like to take the mean of the 3 eigenvalues of the tensor, and that's the typical image. Or I can look of the relative size of the first one to the relative size of each of them to the mean, like standard deviation, and that will give me some kind of how big is the first one versus the other, how different are they in terms of size, and that's we're going to call that fraction anisotropy. That's essentially if we have a ball, fraction anisotropy is 0, and if we have a cigar, function anisotropy is 1. So we can calculate that everywhere in space, and it's actually a beautiful image. And I think white matter just pops out, right? Because where there is white matter, things are really nicely organized and oriented. So the ellipse is more, the ellipse become more elongated, and we get this and it just pops out. So here is, for instance, the corpus callosum. In here again. Okay, so we see white matter pathways like that. And that many people will do many statistics using this image. Very useful. People find it to be correlated across the group, for many cognitive measurement, you would see correlation to FA. So kind of what we saw before, I'm not going to talk about it at all, so I'm just mentioning it now. You remember we look at VBM and we say we can look at this measurement of whatever it is, the gray matter density thing, across a group of individuals, and try to say if it's separating between group, maybe related to some cognitive phenomena or something like that. Many people do that also with FA, and there is great success. That's very useful in order to identify differences between group of individuals, and also correlate with cognitive tasks like, I don't know, face recognition or reading and so on. The meaning of that is still a little bit vague. Why? How much is close to one actually explain the cognition? People would say it's something about white matter integrity. That's what they would say. But it's very useful. If you would read imaging literature, you will probably see that. One more thing that we have with diffusion, because you remember this tensor had also a vector or eigenvector that described the main orientation, so we can kind of color code where this main orientation was projecting in X, Y, Z, and we can. The typical thing is to use green, red, blue to identify a tree brain orientation, and then we can color code the FA map with the color of the main orientation, and that's how we're getting these even more colorful images of the brain, which also help us dissociate one track from the other, or to say where they're going to. For instance, you can see something here that goes in that direction and another one that goes out. Right? Okay, so to summarize, diffusion give us three main measurements. Diffusivity, which have actually units of diffusion, right, of diffusivity. Anisotropy, the FA, how far are we from a ball, between a ball to a cigar, and then also the orientation in each position of where this tensor was projecting or pointing to. And just before we going to the break, what might be a problem? Oh, I'm going to give you a hint. What happens if there is a crossing? What?
If you have it there, it's not going to be in either direction. It's going to be in between them.
It's going to be in between them. That's one big problem, and you're right. So in cases where they are crossing, and it happened to be that there is almost always crossing, unfortunately. The first notion was that it's fine. But it happened to be that probably everywhere we have crossing, some more, some less. And that might be actually one thing that explains the variance between individuals, how much crossing they have. Still on debate. But people now pretty sure that the crossing is something that we can see in many locations, besides maybe in the corpus callosum. So whenever we have crossing, and so we have one tensor that describes this one, right, and another tensor that describes the other one. In the end, we're getting something which is first projecting to the wrong direction, and also might have an FA or whatever. Everything will be wrong here. So it's a good model of the data, just very bad model of the biology. And that's actually a tricky point, because people then will try to make a better and better model of the biology. But the problem is that it's really hard to get better data that will support this more complex model. You see what I'm saying? Because this tensor is still a good model of the data. You can summarize the diffusivity in all the directions. It's going to look like that. It's fine. In terms of like modeling of your data. But in terms of the biology, yes.
Data you get at the level of box cycles.
Yes.
The crossing is not like really much small than the resolution of the box cycle.
Within each box, they might be crossing. So axons are tiny, right? Axons are in the size of micrometer. forks are in the size of millimeter, and bundles we don't know exactly. There's actually debate about that, but maybe in the order of some people suggest like hundreds of microns. So in hundreds of microns you might get actually a crossing inside a millimeter. You might get a crossing off. So then there's different kind of crossing actually, and it's true. You're gonna get kissing, or crossing, or fanning. All of those things that might happen in your these different things that different shapes and orientation within. As long as you don't have one clear orientation in your voxel, you have uncertainty. There is more than one problem, not only crossing actually. Crossing is a big name for many problems of not having the one main orientation in your big measurement. And it's a good time for a break. ונדליק מזגן מחדש, נכון? We're going to turn the aircon again. ההגדרה הזאת של הפוקוסינג קצת מבלבלת. של הפוקוסינג קצת מבלבלת. תחשבי על קונוס של בכל הכיוונים מסתדרים פה להזיק, בסדר? אין להם קצת. עכשיו אני נותן איזה פולס ומציל אותם לכאן. זה לא שאני עושה להם פוקוסים, אבל עכשיו כולם הם עדיין שזה קונוס. קונוס נשאר, אבל כשהוא ביחד למידה על פי XY, הם עדיין נותנים לי סימן קוהרנטי. בסדר? והסיבוב שלהם לא משנה מהבחינה הזאת.
מה היציאה מצד פה? כאילו מה קורה בצד השני?
הם התחילו להתרחב גם בפי XY. אחד מהשני. הם התחילו להתפתח גם בפי XY. ואני מסתובב אותם. אבל זה לא שאני אגמור להם להיכנס לפאזה, כי הם נשארו בפי XY. מה בעצם הפאזה פה? ההיטל שלהם בפי XY קודם היה 0. כי נתלו. זרק אותם לפה. עכשיו אפשר להגיד שההיטל שלהם נתחיל Z הוא 0. אולי לא נראה את זה, לא היה אכפת לי. עכשיו, אם הם יוצאים מבחינת את בפאזה ב-XY, nothing I can do about it. אלא אם אני עושה את המניפולציה, כי הסיבוב שלהם הושיעו אותם באותו פאזה ב-XY. בסדר?
כן.
תחשבי יש עוד.
נראה לי שבשביל הסיבוב הזה צריך יותר להבין את הסיבוב המכני, הקלאסי, של ההולדים.
Le charrette, c'est n'importe quoi. Moi, je m'en fous. Mais attends, montre-moi ce qu'il a fait. Mais je te jure, la prochaine... laisse-moi te le faire la prochaine fois.
Non, mais c'est pas ça.
Non, ah non. Ouais, je sais que j'ai vu que pourquoi moi, on dirait qu'il y a genre qui est plus...
חודשים, תגידי, כשנגמר השבוע של הקלאסרום לפני יומיים, איפה אני אמרת כזה?
לא חשבתי לדעת. מאוד ציני. וכאילו בכלל כל זה כאילו של זה. ואני רוצה רגע לבדוק את המודל. כמו שניסיתי זה מוגבל יותר, אבל זה כבר, כן. יכול להיות יותר הנחות בהנחות.
Mais oui, c'est des malades, c'est pire. Ouais, mais c'est ça aussi, tu sais, tout le code, genre, surnomme
Yes.
comment il active
The bad guy.
Turn on or off?
Now,
turn
no,
off,
now.
sorry, turn off.
You code now?
Yes, it's
Yes.
You know?
We are in short.
You don't know? I'll show you.
Là, je fais l'autre.
I want to do the
Okay, so we ended up with crossing. We ended up with crossing. And just to see it, even in the, so this is 2K. Off again? For a while. Okay. For instance, we mentioned that before. Crossing and kissing, both of them would make the same effect. So if you would look, for instance, here in an area, when we look on T1 weighted, it's very clear that it's a white matter in the sense that it's bright in a T1 weighted. And when we look on FA, it's actually dark. There is like a hole. And the reason there is a hole in FA, which means essentially the tensor is almost a ball, right? So many cases when there is crossing, the cigar shape will change towards something which is closer to a ball, right? That's the notion. And in here we can actually see very nice. We can see here two tracks, the red and the green, just mixing here, right? So also the color code is kind of blurred. You can see it maybe better in there. And in terms of effect, we just see reduction on in a phase. So that's the problem that we are facing. And what might be a solution? Can you think about a solution? Say it's your problem. What would you do? Increase the resolution. That's one option, which is tricky because you kind of can't. No, I mean there are now people try now. There's some efforts. We actually pushing resolution from 2 millimeter to maybe toward closer to 1 millimeter. Still very far from the resolution we need.
I would use information from the boxes around it to see if
Oh. So essentially you would look for a global information to minimize the problem. That's nice. Any more thoughts? Multimodal. That thing we're doing now in our lab, we try. It's very hard. That's for projects in a way. And that's good. So you're going for really the advanced, but the thing that people now trying. What else? Do you have any other thoughts? Yeah, please.
This information you have about the connectivity in the brain.
About?
The connectivity itself in the brain.
That's similar to what's up with prior, biological prior, real prior. People doing that for sure. What else? Any thoughts? What everything here is built on there? What model? Tensor. Maybe we can use two. Why not using many tensors? Why can we do anything about that? Can we fix our model somehow? And if we can fix our model, should we have maybe more measurement to have these more advanced models? So this is a big push in the diffusion field. And so the idea is maybe we should just think about the voxel as a sum of many tensors somehow, and find a way to be able to measure them. Definitely many more parameters. Okay. So there's different trends, different ideas. In general, we can summarize it as maybe a ball and stick kind of idea, in which your diffusivity, the signal that you measure, come from attenuations that come from some balls, some mean diffusivity, some effect like that, and then many sticks, many if you want fibers that are in different orientation, and my signal is the sum of those. So many tensors. I just said it in a different way. No. It's nice because it becomes a linear equation in that way. But there's other approaches. Maybe instead of using a tensor, we're going to use a more complex shapes, like adding what we call the kurtosis. So the tensor assumes some kind of a normal diffusion. We can assume non-Gaussianity in the diffusivity. So adding more parameter to this description of this 3D shape, like kurtosis. So now that will allow us to measure this this abnormal, not Gaussian diffusivity, and that will allow us to better characterize the main orientations in the voxel. Other would use just a different base. The idea to use maybe this spherical harmonic deconvolution. So it's a different way. So you create these harmonic objects. You create the base of those, and then you look for the weighted sum of them that will best represent your signal. Okay, so this is different, mostly mathematical approaches to try to explain this the diffusion data. One important thing is I actually mentioned in here, say high-angular diffusion. For all of those models, you have to have more measurements. So even try and attempt and fit these more complex shapes, okay, you have to have more measurements. So one thing that happens is that people move from the minimal diffusion measurement that is needed for tensor to more and more diffusion measurement, more directions, to try to be able maybe to tease apart this and try to fit these more complex shapes in space. If you would do that, what b-value would you would like? You would like a lower and higher b-value, given what we saw in the beginning. Who want to guess? Want to try and reason about that? Remember the first thing when I increased the b-value and there was something that was popping out? I was saying two things about this image. One, that as we increased the b-value, things were more, the directionality was clearer, right? So in that sense, we really want higher b-values. That we have better chance to have a good higher angular resolution as we increase the b-value, because things fall really fast when you are not in the right orientation. So you can fit these like complex shapes. On the other end, what the other thing I said about high b-values? What happened to the signal? Loss of signal. The SNR is really low. So you're going to fit a really complex model to many measurement, but with a very low SNR. So it is a trait which is like actually a problematic trait. So there's many flavor of these complex models. Really, there are many. There is like ocean of approaches to fit the complex diffusivity in each voxels. Just that's a flavor. One of them called DSI, which is spectrum. They call it spectrum imaging because they try to kind of find all the main orientation that is needed in the Fourier transform in here. In here is the ball of stick that I showed you. The first one is the tensor. Okay, and as we said, the main problem is that they might be many parameters might end up by ill-defined system that we need to fit. We're adding more measurement, but also those measurements are typically with noise, with greater noise. Yeah. So if you would see this term hardy, just so you would know, high angular resolution diffusion imaging. So that's the trend right now. If let's say you are in my field, and you will do just a tensor imaging, there's a good chance that the reviewers say, why didn't you use hardy? So that's become like the new standard in many ways. And so when you're reading, I want you to have this sense of tensor was kind of like the best thing that people that was very trendy for many years, and now these approaches become more trendy, and maybe it's pushed back. And we already mentioned that as we increase the b-value, which is something we need for hardy, for high angular resolution data, we're actually going to lose signal, and some people will actually going to mix different directions, many directions, and different b-values. So they will do like a huge data set of many directions and many b-values. So this very complex, many shells they call it, of diffusion measurements. Okay, just to emphasize the problem of having of SNR, say we have 2 points and we fit an exponent. Okay, that's kind of like what we did before with the tensor, width and width. Now I'm going to I'm going to assume I'm going to have more measurement, and I'm going to fit more than one exponent. Okay, so essentially that's kind of like what I said before. Say I'm measuring in several b-values, and I'm going to fit more parameters now. We'll try that. What happens is that as I'm getting close to the noise, and some of my point might be within the noise floor, right? You remember that there was area that was pop, but many areas just was like we end up in the noise floor. We're gonna bias our model in a way that is problematic, and it's really hard to sometimes to evaluate and to know where we are exactly in terms of fitting these complex models. there was work that tried to evaluate that. There is now more. They tried to ask in terms of cross-validation. What do I mean by that? Do you know what is cross-validation? Okay. Say I measure my brain. Oh, that's true for any measurement actually. Say I measure something. Say my brain once, and then I measure it again. So I can say what is the reproducibility in the data. How good is the first measurement explained by the second measurement, right? So I can measure diffusion twice, each of the diffusion measurement twice, and ask what is the agreement between them. It will give me a sense of the noise essentially. And then I can fit a model, and if the model is good, what it will do to the what a good model do to the noise? It reduce the noise, the effect of the noise. You essentially fit the signal and not the noise, right? And so you would assume that the prediction of the model for the second data will be better than the data to itself. Data 1 to data 2 that's essentially what you have in the data, and if you have a model on data 1, that should be a better prediction of data 2. So you can ask when it's actually useful to move from diffusion, from tensor, to these more complex, more advanced models. And so that's what kind of so we want this relative root mean square, what I just described, to be above 1 to be meaningful. And we're noticing is that and when it's not and when it's below, there is no point to go to this more complex. So first, using more b values and more orientation, you get about 10% advantage in terms of explaining the model, right? You remember I said in the beginning that tensor could be a very good model, although very wrong in terms of biology. It's a good model of the data. So there's only some advantage in this very complex model, and it's only happening in several places. So not always, not everywhere. So there's some so this very complex model, they are limited in that sense. So so having all this very complex data doesn't always actually solve the problem that we were describing. Anyway, that is ongoing discussion in the field, and they push and push back. What I want to describe here, and we'll do it shortly, is this approach coming actually from several groups now, but the people who are starting that is Peter Basser, this is in the NIH, and Yaniv Assaf, which is now in Tel Aviv University, and they say we're going to use all these p values and all these orientations and so on, but we're not going to just feed the signal to this mathematical something. We're going to try to do a biological modeling of the tissue. So they propose these models called Charmed and then Excalibur, and it's very similar to what we had before. They would say there is, but now they will identify this object. There's this prediction, this idea that they are axon, and they have some particular diffusivity which is restricted. This thing means that they're never going to look like a normal Gaussian distribution, and other, which is extracellular matrix, that will be hindered, almost like a free diffusion, and their signal will be the sum of those. And having this assumption, they can kind of with assumption you have less parameters on your model, and they are more and your results are more interpretable. So then they can do mix of several restricted and maybe only one hindered, and you get these funny shapes. And the interesting thing is that if you change the diffusion time, and that's a critical point now. So this thing will be restricted because what I say stuck. Let's see this one. They would assume it's stuck within the axons. So if we will release that and change the time of diffusion, in different time of diffusion, different axon bundles will show restriction diffusion, and that will be a function of their axon diameter. Okay, so now they say we have this model that allows us to go and look inside the distribution of size of axon. I will change the time of diffusion. In each time, as I'm increasing the time, more and more axon will appear as restricted. But in a very short time, only very small axon will look restricted. Or the other one, I don't have enough time to actually eat the boundaries, and so it appeared to me like hindered or maybe free. Okay, so with this thought in mind, they build this model, and they name it X caliber, measuring the axon caliber. Okay, and they change the term instead of using B, which also include the time of diffusion, right? The time between the gradients and the time that they open the diffusion, that become now a parameter in the model. So they define something they call Q. Actually, it's actually wrong. People first define Q and then define B, but in our story, we first define B and then Q. But using this Q term, okay, so the diffusion terms are parameter that they will also change in the measurement. So they're adding another thing. Before we change B value in orientation, now they're also changing diffusion time, adding one more dimension to the problem. But they say this is really interesting because that will allow us to look on this restricted diffusion of these axons. And they can show that this is postmortem. Let's say they take two type of axons, put them in the magnet. They do the histology. One of them is the histology. I will guess this one is the histology. So they have this different distribution of sizes. And then with diffusion measurement, they can actually replicate the distribution of sizes between these two different nerve bundles that they put inside the magnet. And then the next step they did is to do that in a mice along its corpus callosum. And along the corpus callosum, there are different axon bundles which have different sizes. Do you know why? What is so unique about the corpus callosum? Question in biology for a second. In biology. Because it connects the two hemispheres. So it's a very small area, but we have fibers that are arriving really from different locations. Right? There is like axon that's coming from the front, and axon that's coming from motor areas, and axon that's coming from occipital vision areas. And they have different properties. So we have a really small area, which all the axons are oriented in the same orientation, but in space they are separating according to systems, if you want, in the brain, and they have very different properties. So it's a great model area for all those kind of works. Okay, and so they use this area in the rat. I think mice or rat. I think it was a rat. And so they did histology, they find the distribution of sizes, and they can show that with their measurement, okay, this is actually their measurement already, they can actually be sensitive to the change in the distribution of size of axons. So it's pretty amazing. There is now huge debate about where this thing is coming from. But there is a lot of beauty in the model anyway, and the idea that you can use this very coarse measurement of diffusivity, and suddenly you get a measurement of this really microstructure phenomena with axon sizes, and knowing the axon sizes would say a lot about conduction velocity and so on. And you can ask Shai how much he would like to have a good measurement of axon sizes. That will change her thesis, her PhD. Okay, so this was done in mice. There is now attempt to move it to humans. It's hard, mostly because it takes a lot of time, and doing a very short diffusion time. Also, it's creating a lot of there's the issue of SAR. SAR is how much energy you actually transfer to the tissue. So there are issues in here, but the direction is really promising and interesting. There are many. There's other flavors that I'm actually going to skip. I'm going to skip that because it's kind of saying the same thing. And now I want to move to the last part of this talk, which is the thing. So people using diffusion for two main things. Either to measure some kind of a microscopic measurement of the tissue, like the FA, and compare across subjects. And the other main use, which you saw a movie about, was identify what? Tracks. Right. So assuming we have a good model of each voxel, we can try to find tracks. And you saw this talk of Susumu Mori, which he built the atlas, the first atlas of the human brain with the diffusion. And the thought is like that. We have tensors, right? In each voxel we have tensor. They have main orientation. We assume that the main orientation is fine. And it's actually, in some places, it's actually pretty good. And then we will write an algorithm that's just going to connect the dots. Okay, here is like a bunch of tensors, and we will connect the dots, and by that we will kind of identify a white matter fiber, a white matter bundle. Okay, important that we're not really measuring axons. Some people make this mistake. This is not a measure exactly of axons, but we hope this is a measure of some kind of aggregate effect of many axons, which we call fiber. And there are now billion tools for that. If you ever need them, here they are for you. So let's just think about what was happening in here. We took the tensor, we defined the principal diffusion orientation, or the PDD. Okay, and then we can do, and then we track. We do tractography. That's the name. We start somewhere, and we jump to the next station. The next station, we have some assumption, like for what is the angle that we should do, and one important, and when should we stop? We have a stopping criteria. Maybe it should stop always in the gray matter. Maybe it should stop when the phase is too low. There's different routes. Maybe we have to stop if the angle that we need to jump next is too big. Things like that. Also, there's important two flavors. One of them called deterministic, which means that from each point there is only one favorable point to jump to. From here, I will jump to here. That's the most reasonable jump, and so that's the one I will do. And so it's deterministic in the sense that if I will do it 1,000 times, I will get always the same thing, assuming I will sit from this position. And the other one is probabilistic. It's a probabilistic assumption. Say, I'm not sure. So I will define each voxel as a map of directions, and they would have different probability according to the diffusion signal. Assuming we have different models, they kind of, you can think about them as now as probability maps of where the diffusion is going to, where is the main orientation, and I will jump. And so my next jump will be some calculation of where I am and what is the probability to go to the to accept in the next box or something like that. So this is a probabilistic tractography algorithm. And so what happened in the end is that we're getting these beautiful pathways. Actually, given all the uncertainty that we had about the voxel, we're actually doing pretty good in identifying the main white matter pathways. Well, so that's essentially that's what we said. I don't think there is more in here. And so let's see, and that's something that was, I think, in the question. Can we use any kind of information to actually identify the pathway? So we have now many bundles like that. We did tractography, let's say from here to here, and we sit in here. Let's say we sit in the occipital, okay, this occipital cortex, and this is all the track that I found. I found some that goes to here. I found some that goes there. How would how can I identify them? And so what I can do is use other information. I would say that corpus callosum tracks are the one that goes through the corpus callosum. If I need to define the corpus callosum in each subject, and then I can sub-select the one that goes through the corpus callosum. So we start in the occipital, and now I'm also adding the corpus callosum, and so I'm identifying the corpus callosum, and maybe I remove the others. Okay, and so I'm getting this callosal fiber of the occipital cortex, and I can also say where it was exactly crossing within the corpus callosum. There's a lot of information that is very useful in terms of the biology, and I can do it with many planes and put different planes in space. That's what we have in the atlas. We're putting planes like the corpus callosum, or with the corpus callosum in this case, and then we can segment the corpus callosum. In this case, first find the corpus callosum pathways. So we discussed before that there are different callosal fibers for different systems, so we can find them, and also can see how this how the corpus callosum is separated in each individual. So that's an example of things we can do. We essentially getting maps of tracks. We can get a map of about 20 tracks in each individual with diffusion data and with these priors, and comparing this to the atlas. And then we can use, and this is different methods, different flavors of how people are doing that. And then what they typically would, or something will do, they also would look on the, say they find the track here, this one. They will go and ask, what is the FA, the functional anisotropy, along the track between individuals, and maybe compare it between one group to another group and so on. So that gives us a tool to look on say the FA in a particular track, the SLF or the ILF or whatever you care about. Okay, some problems of tractography is this. So you would like your model to be equivalent in both directions, right? You would like to say you start in A, you arrive to E. If you would start in E, you would like to go to A. But that's actually not the case. As you can see here, because the tractography, why is it? Can anyone think what is the problem here? Why that? What's inherently broken in the system? Anyone, any thought? Yes, the second part of your answer, the first word you say, it's not continuous, it's the answer. And some of you actually suggest that as a solution before. The fact that we're doing it, it's a local calculation. So my local calculation in A pushed me here, but my local calculation in E drove me to somewhere else. So because this algorithm is local, then we have this problem. Okay, so we're giving really a lot of weight or important, yes, or information to the local calculation. So it's become that's what he's saying here. It's become very greedy and use local voxel information. So that's a feature or problem of the tractography algorithm as most people use. And we don't use any global information in this approach. Another problem that you might ask and check is how can we validate a result, and it's really hard to validate it. Actually, we don't have many gold standard measurement of how long pathways look like, and so it's very hard to say, yeah, are we right, are we not? So this is kind of the issue. So some people would say the solution is just using probabilistic tractography and very complex models, and then shouldn't be a problem anymore. That's one approach. And then we're going to get this kind of heat maps of the brain, and it's not going to be very greedy because we'll run it many times, and sometimes, well, it'll be local, but we'll kind of, the fact that there is more than one possibility will be emphasized in this probabilistic approach. And that's, for several years, that was kind of the direction that the field was going at. And still many people think this is the solution. And one of the things you get when you do that is that you get a huge difference between what was the main method in the beginning, the deterministic one, to probabilistic. Suddenly we get like bushy, huge fibers that connect everywhere to everywhere as you allow this probabilistic approach. For instance, this is the arcuate fasciculus that is important for what? Arcuate fasciculus, anyone heard about this track? Yeah, that's the connection between Wernicke and Borka. Super important track. And with this, so in one hand we see it, we can identify it. On the other hand, we change the algorithm, and we get very different results. In this case, it actually never reached Broca. It stopped just before in the motor cortex. And in this case, it's just covering the whole brain almost, so almost the whole front track. So So in terms of where they project, really change. Also, when people went and checked, so there was then phenomena in the field when the field start to eat itself from inside. It's interesting to see it in terms of culture of science. And in diffusion, there are the different fields have different culture. Some that they're hugging each other, others just not so much. So in here, this was an interesting work, which essentially say everything is wrong. What they did is they compare diffusion result in monkey to tracing result in monkey, and try to see if things actually arrive to where they should. And they say no, it's never. And no matter what method we're using, it never reach the right place. In the case they checked. And then there was another one like this one that was. This is when it was in the archive. It's now published in Nature Communication, I think, which essentially show that. And what's interesting about this work is that everyone in the field is on it. It's like hundreds of people here. Everyone who's doing diffusion is in this article. And essentially what they did is say, okay, we're going to create a synthetic data set which would look like diffusion, but and then each one will run his algorithm and see what we get. And what they got is that they're always getting false positive, because everyone moved to this probabilistic approach, which is very allow many fibers. Now they just everyone fails all over. So in terms of false positive, do you know the difference between false positive and false negative? So in the beginning they kind of miss fiber, and now we like have too many. Yes. Yeah. Yes, but the problem is that you don't know how to choose it. And so each of them will say that they know how to choose it. I have my trick, I'm going to do it like that, and I had my regularization of my probabilistic algorithm, and I will get it right. The answer was that nobody got it really right. There was some were better than others, but in general there was nothing that was like, okay, it's working. There are problems with this work. They didn't use the most advantageous data and so on. So there are problems with this work. I mostly want to give you the flavor of some uncertainty and unrest in the field. Something is going on. One direction that was mentioned already, I think by Levy, is using the global information. So that kind of was missed until now. And so can we use that? So there are those approaches called global tractography. And some people think this is the future. And so in here, instead of doing voxel by voxel, we try to fit. In terms of fitting the problem, it's like it's painful, and it's really hard to find where you start, how you get to a global solution, and so there is many problems in fitting here. Like it's terrible. But at least it's using the whole information in order to identify pathways. So that's a good direction. And there is one more direction which I like, and came from the lab that I was doing my postdoc, but not my work, which is this. Well, they were saying, we're using this data to create fibers, right? That's what we're doing all the time. No matter what tractography algorithm we use, can we go back and try to check if we overfit? Let's just do validation with the data. We just check if this data can now predict. We're doing this local greedy thing, which we kind of like getting farther away from the data, right? So we can say, okay, let's go back and check now that we have this thing. Let's call it a prediction and see if it's predict the data. And that will allow us to remove many false positives. That was their approach. Okay, so going back, and nicely, because if you remember, I showed you this ball and stick approach, which was essentially a linear model. So okay, we can write a huge linear problem, which each fiber is a predictor of the signal, but all over the volume. And we can try to solve this problem. Okay, so it's a linear problem that is solvable. It's big, but so you need techniques to solve huge linear equation, but you can solve them. And what they discovered that about 90, I think. So essentially, if you have a weight of 0 on a track, it means that it doesn't contribute anything, and you shouldn't use it. You should remove it. And what they found that about 90% of them is actually getting a 0 weight in using a typical probabilistic tractography. So kind of they remove tons of the fibers. So they actually not contribute anything, just not use them. That's a nice way of validating the data within the data. And there are more approaches like that. And this one is interesting because it's doing this approach, but also try to add the biological information that I showed you with the Excalibur. So in this approach, so other approaches, new approaches, try to use both microstructural axon level information and predicting the signal using these two ideas together in order to fit the model. So that's an interesting direction that the field is taking. I would just mention one more thing. The other thing that people try to do is using really high resolution, you mentioned, on monkeys. So here you can scan them forever, and when you scan forever, you can get beautiful data, and then that's creating a data set that you can actually validate things, because we're actually missing a tool to validate. Right? You see here this beautiful RGB image, right? And now things are really distinguished really nicely, and you can check if whatever algorithm you develop or approach you develop actually can replicate this thing, say if you undersample the data, so what actually done in humans. Okay. Any questions? Any thoughts? No. Okay. So before I'm ending, I'm going to say one more thing, which is like I didn't know where to push it, so I put it to the end, but I have time, surprisingly. So I would just say, just to mention that because we're using diffusion, and I was mentioning that there is the diffusion itself has some art, because it's a method, of course. I would just say something about artifacts that exist in diffusion. And so there are two main artifacts in our images that we should be aware of, and be sensitive not to interpret when we see results or changes in there. So what you see in here, and you don't see so much because of the screen, is that this part in the front is just missing, just fall. And that has to do with the way we scan the brain. That's something so using this fast approach to measure K-space, to measure the image in space, there are areas which we have a very, we're getting a very strong reduction of signal because of inhomogeneity in the B0 field, so the magnet and the fact that it's close to the sinuses, so close air-brain interface creating these artifacts in the magnetic field, in the homogeneity of the magnetic field, and we're losing signal. So it's really hard to track from here or to say anything about what we see, for instance, in here. There are solutions for that. That's something to note that might happen. Other thing that might happen is because we're using these gradients, we're actually creating more echoes called eddy currents. We're creating more currents or more echoes in the system than we actually thought that there is in there. And that's kind of shifting, if you want, the image in space, or changing the diffusivity measurement. And that's another another artifact in diffusion that people in the beginning ignore, and now realize that they have to take control before they do this complex modeling and try to say something about orientation. There are things that's happening just because of the measurement that change. We change our understanding if we want correct for them. Okay.
Remind you that next class is a lab.
The lab class. Laptops.
And I will also post on forum something to discuss with
Everybody heard? There will be data to download, and it's going to be Kirgul, and bring your computers. And thank you. Enjoy the weekend.